Hello everyone, welcome back to another video. This is Pranav, and in this video we'll be discussing about the topic typical ResNet architecture. So coming to the introduction part, ResNet basically stands for Residual Neural Network, and then it was introduced by Microsoft Research in the year 2015. ResNet is also known for its ability to train very deep neural networks effectively, and we have a representation of the ResNet architecture on the right hand side, where we have the 34 layer residual image that is given as an input, and then we have multiple convolutional layers along with the pooling layers to have an output. So the motivation for residual learning is that in traditional deep neural networks, they suffer from this vanishing gradient problem. That is, when we have loss function, the gradient is drawn, and then we don't have a particular loss function that is complete. So for this, to overcome this, residual learning basically aims to address this issue by using shortcut connections. That is, these shortcut connections allow the network to learn the residual functions that are lost, and then basically these are in the hidden layers. We can see on the right hand side that we have three input nodes, that is x1, x2, x3, and then we have the hidden node layers. So these have these links that are particularly arranged inside the hidden node layers, and then the output neurons give out output of y1 and y2 based on the configuration. So this is how a basic layer connection works. So the building blocks of ResNet are that the ResNet is itself a residual block, and then a residual block consists of two convolutional layers with a shortcut connection, and the output of the shortcut connection is added to the output of the second convolutional layer. So we can see that on the right hand side we have two blocks, wherein the first one has two particular layers with a shortcut connection of convolution 1 cross 1 and batch normalization, and this output is added to the next one to get the output of the second particular block. So coming to stacking residual blocks, ResNet architectures typically stack multiple residual blocks. So deeper ResNet models have hundreds of layers. As we know, there are many types of ResNet architectures as well, ResNet 50, etc. And on the right hand side, we see an image where we have three particular strides, and there are multiple layers of convolution and then pooling layers. So stacking residual blocks allow the network to learn complex features, and these features are performed or learned in the hidden layer functions. So skipping connections. So skip connections in ResNet allow the network to bypass one or more layers, and then skip connections help with gradient flow and alleviate the vanishing gradient problem. So the issue we see in the vanishing gradient problem is basically skipped uh, in such a way, or is avoided in such a way that these particular layers or the skip connections allow for it to plot all the particular nodes, and then skip connections enable the training of very deep neural networks. So we can see on the right hand side diagram representation of the skip connections. So we have starting from the bottom end, we have one particular layer, and then we have convolution and pooling. So we have direct skip connections between one block to another block, such that it performs better, and on necessary requirements it performs in the lower level as well. So residual learning concept. So in residual learning, the network learns residual functions instead of directly learning the desired underlying mapping, and then the difference between the input and output of block is the residual function. That is, we have an input x, and then we have a weight layer to which we have an activation. So identity mapping, as we saw in the first point, is basically what it learns in the first, and then we have that is known as a function, or we have residual function called f of x, and then the weight of that particular function, that is f of x plus x, is added, and then we have an activation function. So what this does is basically it simplifies the learning process, and then it improves the performance of each and every layer. So types of resonant architectures are they come in different depths, and then they come in different variations. So basically, we have, for example, we have ResNet 18, and then we have ResNet 50, we have ResNet 101, and then 152. The numbers represent the number of layers and also the configurations of the type of architectures that are going to be selected. So deeper ResNet models tend to have better performance but require more computational resources. As we know, each and every layer, for it to be pulled and then for it to be trained, we need better resources, that is GPU, CPU, and memory. So those are the requirements. And then the choice of ResNet architecture depends on the specific task and dataset. So we might tend to choose a lower version of model for it to perform a slightly small task, and then we can go ahead with the bigger architectures when it comes to performing greater value tasks. So training ResNet models. Uh, Training ResNet models requires a large dataset and significant computational resource, as you just saw. And then techniques such as data augmentation, batch normalization, and then learning rate scheduling are commonly used. So basically, what this does is it makes it easier for the architecture that we use for to apply all the particular pooling and then uh, functions that it has. So data augmentation, once performed, it makes the complete data set that we're going to use in a uniform way, and it has a better learning rate compared to a non-trained one. And then pre-trained ResNet models are also available for transfer learning on new datasets. That is, ResNet models are already trained, and then these can be used to implement it on a particular small set of dataset for it to perform better in cases of language models or in cases of object detection. So these can be used. Coming to benefits of ResNet architectures have been widely adopted in various computer vision tasks, and then such as object detection, as you just saw, or it is also used for detection, iris detection, and then basically all the computer vision tasks that are related to it. And then recent models have achieved state-of-the-art performance on image classification benchmarks. That is compared to all the other models that are available in the particular scene. So ResNet tends to perform better when it comes to image processing or image classification benchmarks. So ResNet skip connections and residual learning concepts have influenced the design of other neural network architectures as well. So this is where it mainly came into play initially, and then it was also used on other model architectures as well. Coming to applications of ResNet, image classification being the main one. ResNet models are widely used for image classification tasks such as identifying objects or scenes within images. They have also achieved state-of-the-art performance on benchmark datasets like ImageNet. So also, object detection is also one of them, wherein ResNet serves as a backbone architecture for many object detection systems, such as faster RCNN, that is, and then we have YOLO, you only look once. We have SSD, that is single shot multi-box detector, and the deep features learned by ResNet are crucial for accurately localizing and classifying objects within images. So also transfer learning is one of the main applications in ResNet. So pre-trained ResNet model, as you just saw in the previous point, we have benchmark data sets like ImageNet that is already pre-trained. So these can be imported into our modules, imported into our code as modules, and then can be trained on other datasets that we tend to use or we need output on. So once these trained on large scale datasets like ImageNet are commonly used as feature extractors for transfer learning. So by fine-tuning these models on smaller domain-specific datasets, one can achieve good performance with limited labeled data. In conclusion, architecture has revolutionized deep learning by enabling the training of very deep neural networks, and also the use of skip connections mainly, and residual learning has proven to be effective in improving gradient flow and then learning performance. So ResNet continues to be a popular choice for various computer vision tasks due to its performance and versatility. Thank you guys for watching the video. Hope you guys liked it. Please do leave a like and subscribe to the channel.